Okay, I had made an error in class today, so I wanted to clear this up on the worksheet 7B. So I wanted to work through that example so that we can have everybody on the same page here. Alright, let me make sure I've got my pen. There we go. Alright, so we've got a beam. We have distributed load W acting along the length of that beam. We have a reaction support here, a roller support at B, so there's only going to be a vertical reaction at that point, By. We have a pin support here, so we can have AY and AX at that location. And we're going to determine the shear and moment diagrams for this beam. So if you recall, our approach here, we're going to 1. Find the reactions. 2. We'll section the beam at each discontinuity. 3. We'll solve the equations of equilibrium. 'And what we're looking for there is we're looking for our shear V and our moment M. And we'll solve these. This will be in terms of X. So that will mean we'll end up with a set of equations for V versus X. Oh, there's X. And M versus X. And then 5, finally we will plot those equations and M versus X. Alright, so our approach, we're going to find our reactions here. Hopefully everyone is able to do that. So step 1, reactions. What do we have? So over this whole length we have this distributed force, or this distributed load W. It's acting on a length A plus A, or 2A. So step 1 here, we're going to have our resultant force of our distributed load. It's going to be W times 2A. And where will that be acting? Well, this is a nice constant load, so it's going to be acting right at the midpoint of that load. So it's going to be acting at A. So there's that resultant force. So the next thing we can do is we'll take the sum of the moments around A, set that equal to 0. So what do we have acting there? So AX and AY will both not contribute to that since they're passing through that same point. BY will be acting at point A, and our resultant force due to our distributed load W will be acting at point A. So we'll take up that sum here. So it's going to be 2AW. That's going to be a clockwise moment, so it's going to be a negative moment acting at A. So we're multiplying, this is our force, multiplying by our distance here. And then we're going to have plus BY, so that's our force, acting at A. That all equals 0. So BYA equals 2A squared W. BY, just divide by A on both sides, equals 2AW. So there's our reaction force in Y. It's 2AW. I'm just going to put that up on our diagram here. So we know we have this resultant force acting down here. 2AW, our reaction force at B acting up is 2AW. Now we can take our sum of our forces in Y and in X to find these last two resultant forces at A, or reaction forces at A. So sum of the forces in the Y direction equals 0. 0 equals negative 2AW plus 2A, make that lowercase a, W plus FAY. It's pretty obvious. This negative 2AW and positive 2AW cancel out. So FAY equals 0. And the sum of the forces in x equals 0. Again, looking at the diagram, we have no x component of our load. We have no x component in our reaction at B, so we must have FAX equals 0 at that point. So 0, the only x force is FAX, so FAX equals 0. So there are reactions. Cross that off. Next, we'll section our beam at the discontinuity. We talked about what a discontinuity is. It's anywhere we have a concentrated load or reaction along the length of that beam. So we'll section our beam into two parts since we only have the one discontinuity at B. So here we're going to have, this is going to be 0 is less than or equal to x, which is less than or equal to A. So we'll leave off that reaction at B at this point. I should have maybe given myself a little more room here. But I have this distributed load W. I have FAY here, FAX there, and then I'm going to have my shear V and my moment M. I'm drawing these in the positive sense, so if I find a negative value, it just means it's going the other direction, and when I plot that out, I'm going to just be below the 0 horizontal axis on my shear and moment diagrams. Again, positive shear gives us rotation clockwise, and a positive moment in the section approach here is making this beam smile at us, get concave up. So on this end, on the right end, it's going to be up, so counterclockwise. When we take our sum of our moments or sum of our forces, we'll use the normal sign conventions that we have for those approaches. So here's my free body diagram of this. This is going to be Wx, and this length here is going to be x over 2. So this distributed load, the magnitude of that is going to be my load per meter times our length. So the length of that section is W times x is our length, and it's acting at the middle, so x over 2. My shear is here, my moment, and FAY is 0 and FAX is 0, so we can do our equations of equilibrium here. And this might be where I made a mistake in steering us wrong. So I'm going to take the, if I take my moments about this point over here at x equals 0, the sum of my moments at x equals 0 is going to be a negative moment here, right? So it's going to be creating clockwise rotation about this point. So it's going to be negative Wx times x over 2. And then I also have the contribution from my shear here is going to be also a clockwise moment, so negative Vx, and then plus, so this moment here is counterclockwise plus my moment. So if I'm taking this at x equals 0, this should be the approach. If I take some of my moments at x, so at the end of this, the shear component goes away. This changes signs. Now I'm rotating counterclockwise around x. So I'm going to have Wx times x over 2. So this distance here is still x over 2. Here's x. And I still have my positive moment here. And that's going to equal 0. Give myself a little more room. So m equals, so moving that to the other side, we have Wx squared minus sign over 2. So there's that part of it. My shear, I'm going to find using the sum of the forces in y equals 0. So I have 0 equals negative Wx. Let me make that a negative sign. Oh. Sorry about that scrolling. I'm going to make this say negative sign. So I have negative V. Right, so this is going down. My Wx was going down here. So V equals negative Wx. So those are two components there. My other section of the beam. So now I'm looking at a section from 0 is less than or equal to, A is less than or equal to X is less than or equal to 2A. So I have, this is going to be Wx, and that's acting at, it's going to be x over 2 on both sides of this. I didn't quite draw it that way, but you can bear with me. I'm going to have By at this point. Here's my shear, my moment. So on this side, I have x minus A. And this side down here, I have x. If I still had an A reaction, I'd show that on this. So in this case, my moments again, I'm going to add those up to 0. So I'm going to be taking it around, if I take it at x, some of the moments at x equals 0. So looking at this point, I'm going to have a positive 0 equals Wx times x over 2. That's causing a counterclockwise rotation. And then I'm going to have a negative By times x minus A, so it's operating at this point, plus my moment at the end. So I have Wx squared over 2 minus 2by, and 2by, as we found above, is 2aw. So I'm going to have minus 2aw, that's my by, times x minus a plus m. So if I slide both of these over to the other side and flip it around, I get negative Wx squared over 2 plus 2aw x minus a. Now if I expand that out, m equals negative Wx squared over 2 plus 2awx minus 2a squared w. Alright. And then finally, some of the forces in y equals 0. I think I can squeeze that in here. So 0 equals negative Wx plus by, which is 2aw, and that's positive, plus v equals, what do we have, Wx minus 2aw. Alright, so we have those parts. So I solve that. I'll show you in a moment what happens if I take my moments at 0. I can still get the correct thing. So I did my sections, I did my equations here. So I found equations of v versus x and m versus x. Now we can plot those. So what we'll have is a discontinuity at a between the first half and the second half. So this part, so like this value for shear is only active after a, and this moment is also only active after a. This part stops being active after we get to point A. So step 5, plot. So if I have v as a function of x equals negative Wx, and that's from 0 to A, and v as a function of x equals, how did I get that? Did I make a mistake still on this other part? Oh, this should be negative here. Sorry, I still made a mistake here. Negative, so I should switch these around. Negative, my v is acting down, so it should be negative here. not a positive. So when I slide it over to the other side, it becomes positive, keeps that the same on that side, excuse me. So I should have that same slope, so I should get negative wx plus 2aw, and that's from a less than or equal to x, which is less than or equal to 2a. And then similarly, my moment of x is going to be, we have there negative wx squared for my part from 0 to a, negative wx squared over 2, that's from 0 to a again. X here equals, what do we have? Negative wx squared plus 2ax, negative wx squared over 2 plus 2awx, and minus 2a squared w, minus 2a squared w. That's for x greater than a. Alright, so we can plot those out. So here's v. Oh, that was supposed to be vertical. Here's my x direction here. So I start out at x equals 0. My shear is 0. Goes down somewhere. Here's point A. And then, so that's the first half of that. So what is that going to be? This is going to be WA. And then at 0 here, or at A here, I get 2a squared, 2aw minus WA, so it's going to be positive WA, and that's going to continue on until I get to when x equals a, it's going to be 2a, excuse me, that's going to be negative 2aw plus 2aw is 0. So this is at 2a, and this is my shear diagram. I'll do my moment right next to that. Here's x, here's my moment. So at the first half, up until point A here, maybe should have put that on the top, I'm going to get negative wx squared over 2. So at 0, that's 0. It's going to be increasing negative until we get to A, and it's going to be a parabola shape, right? It's x squared. It's going to be an exponential function coming down here. So at A, this equals negative WA squared over 2. And then once I go beyond that point, I use this second equation here. So if I fill in 2a here, I get negative 4a squared w over 2, so negative 2aw x, 2aw squared, there's that. This will also go away, so I just get the reverse of that here at 2a. So there's my moment diagram for that. So hopefully that makes a little more sense. Let me break down a little bit where I made my mistake before. So if I look just at this, let me take a look at this section here when I do my moments on this section between A and 2A. So moments for section x is greater than A. So if I have that section again here, I have some, this is wx at x over 2 is my by, this is 2aw, this again is x minus a, this is at a, my v, my m. Alright, so I could take my moments around 0. This is where I'm trying to clear things up from how I did it. This is my mistake in class. If I take my moments at x equals 0, what am I going to have? I'm going to have a negative moment from this distributed load. So I'm going to have negative wx times x over 2. And that was a clockwise, so that's the negative sign. This is going to be a positive moment, plus 2aw times a. I have this moment here, that's going to be a positive moment, so plus m. And then this component from my shear, this is where I made my mistake, is the shear is going to also create a moment around x equals 0. So I'm going to say, and that's going clockwise, I'm going to say negative v x. So it's acting at x, v is at that point. So if I expand this out, and that all equals 0. So 0 equals negative w x squared over 2 plus 2a squared w plus m minus, I'm just put my x here and put my v out there. So if I come back up and find my shear for that part, is negative wx plus 2aw. Negative wx plus 2aw is my shear from that at that point. So if I expand that out, negative wx squared over 2 plus 2a squared w plus m, make that a positive, wx squared, so that's this term, minus 2a wx. What do we have here? Let's pull the everything that's not m to one side. So here's m equals, I'm going to have positive wx squared over 2 minus 2a squared w minus wx squared plus 2awx. So I just pull all these onto the other side and flipped it around. So I have wx squared, wx squared. I can add those together. Negative wx squared over 2 minus 2a squared w plus 2awx. That's my moment at the end there. So the mistake I made was not accounting for the shear contribution to the moment. If I compare this to my previous value for moment at that point, let's see what we've got. So we've got negative wx squared over 2 minus 2a squared w plus 2awx. Let's come back up here. So I have negative wx squared over 2 plus 2awx minus 2a squared w. It's the same thing, I just had this term there and vice versa, but everything worked out. So that's where I made my mistake. If I sum at the point where I'm taking the shear, I don't have to include the shear in my moment calculation. If I take it at the other end or another point, I will have to include that. So hopefully this video clears that up for you, as well as gives you a walkthrough of how we make that shear and moment diagram.